Right, good morning, everyone. Unfortunately, the issue that was going on Monday is still persisting, so I have very little energy and mental capacity, but the good thing is, once again, I do have those previously recorded lectures, so instead of doing it live, you will be getting 95 to 99% of the exact same material that you would have seen anyways. And just remember that any dates that you might hear during this video, if I say something about a Tuesday or Thursday, ignore it. If you hear something about an April date, ignore it. If I say something about the final exam that is not this exact detail up here, then you ignore it. I know the last video I played for maybe 10 seconds too long, and you might have seen something about a final being in April or, you know, a slightly different detail, whatnot. So please just remember that for the final, it's going to be 25 questions, and it's cumulative. It covers everything from the first day of 1.1 up until wherever we finish in 4.3, which will be maybe 15-20 minutes into the lecture today, roughly. So I will still be going over almost all of 4.4 today, and by I mean me, like 8 months ago. And then we'll stop with maybe a few minutes to spare. But I will not test on it since it's the absolute last thing right before the final exam. I don't think that that would be fair. I will not make that homework graded, but please understand that if you're going on to calculus, that material can be important. So there's a reason I'm still giving it to you, even though I'm not putting on a final exam. It's important. Solving logarithmic and exponential equations is important. If you're going to do anything with chemistry later, it could be important in there as well. And I think they tend to have the simpler examples that we see, but still the same concepts. So nothing should be surprising in terms of the test format. You get an extra 30 minutes since it's a few extra questions. I figured that's fair. No notes, no books, no internet. You can use a calculator. Remember that you should be showing all your work and submitting it in Canvas within 15 minutes. No work means I can give you a 0 on the test if I choose to. If you need any kind of partial credit, I will absolutely defer to the work. No work means no partial credit, per usual, and then you email me and let me know, which y'all have been doing a good job of throughout the semester. Please remember that the final is weighted the same as the rest of the tests. Test 1, Test 2, Test 3, and the final are all 20%. Your My Math Lab homework is 20%. And yeah. The review is available. It should be the very last thing you see in My Math Lab. You can also review the previous tests and previous reviews. Basically, the final exam is going to be composed of stuff from Test 1, Test 2, Test 3, and then some stuff from Test 4. So those would all be good resources. Remember that your final exam is one day only. I will not allow any finals taken on the 15th. I have to start getting grades in and ready to be submitted by the night of the 15th. So I can't do the exam late. If you're late, it's late, and that's it. We will not have class on the 14th or 16th. Once we take the final, that's it. So you've got time to study. You've got time that would be normally in class to take the test if you are available at that point. But please remember that this will close at 11:59 p.m., no exceptions. So if you have any questions, please email me. I will check the chat at the end, but I can't really check it too much while the video is playing. Otherwise, stuff will be popping up on the screen. But yeah, I can always answer questions in post, and then this will be up on YouTube and in Canvas later. All right, so it has been an absolute pleasure. I hope that we have all been able to learn something in this new format. I know it's very different than being in person, and I know for some people it doesn't work as well, but I hope I've made this as manageable as possible. I hope that you're able to retain this information to use it in your next math class, assuming that you have a next math class. Again, most people don't stop at pre-calc, they go on, and you need a lot of the stuff from this course. And I think I've been very emphatic over the material that you need. All right. So let's tune in for our last class. Again, it's been a pleasure to help y'all. Maybe I'll see you in another math class down the line.
Then we had the power rule, which, you know, the expanded version doesn't really look expanded, but we said the condensed version has everything inside a single logarithm. In the expanded version, this p is outside of it, so that's why we call it expanded. And we said that this was a helpful property to simplify a logarithm, arguably. If your bases of the log and the exponential don't match, you can at least bring the power out, and then good things can happen. So we made it up to example 3, A, B, and C. We still have one more to do, and that is D. Let me pull up my file. There we go. D. I think I mentioned that when I got all my notes out of my office, which I'm not allowed to go back to, I was missing the chapter 4 notes, but I have a digital file of it. So I took pictures of it on my phone, and I'm just looking at my phone for these examples. If I didn't mention it, there it is. Good times. So 1/2 natural log of x plus 1/3 natural log of 27 plus 2 natural log of y. The first day I did it, I had my other half's computer with the file, but it kept closing and I needed her password. So she had to come back and help. So I was like, nah, this is silly. Let me just take pictures. 1/2 natural log of x plus 1/3 natural log of 27 plus 2 natural log of y. Not that y'all cared about my complications. It's just fun to talk about. So we are trying to condense. This was to condense. So we want this to be a single logarithm if possible. Remember, it's not always possible. If they have different bases, you're stuck with multiple logarithms. You'll be able to condense some, but not all. But these are all natural logs, so we can make this a single natural log by the end. But before we do that, we can't have coefficients because these all need to have matching coefficients, preferably a 1. Notice I said preferably. We can make this a little more complicated, but we won't do that. So let's bring the exponents up, the coefficients up as exponents first. So this will be the natural log of x to the 1/2 plus the natural log of 27 to the 1/3 plus the natural log of y squared. Now, you might think, oh, x to the 1/2, I can't do anything there. 27 to the 1/3, I can't do anything there. Y squared. You are correct that you can't do anything there, but the others you can. You need to remember that fractional exponents are radicals. So this is probably the 10th time I've reminded us of this property, that some base raised to a fraction, let's go x to the a over b. This is the beef root, sounds like beef, of x to the a. The denominator becomes the index, the numerator the power. That's an a there. So we're going to need to rewrite these things, and I may have said that the x to the 1/2 can be simplified, but we're going to be able to do one thing, but not as much as the middle term. So let's rewrite this as the natural log, wrong color, of the square root of x plus the natural log of the cube root of 27 plus the natural log of y squared. The reason we've done this is because the middle one is simplifiable. The cube root of 27 is 3. So this is the natural log of the square root of x plus the natural log of 3 plus the natural log of y squared. I think I had a minus somewhere in there. Doesn't matter, I don't. Now these are all positives, these are all pluses, so we can just condense this as a log of a single product. So everything's going to be multiplied. No denominators because there's no subtractions. And inside, you'll have the square root of x, the 3, and the y squared, but we definitely want the 3 first, so I'm going to write the 3 first. Then the square root of x, then the y squared. And this is our condensed single logarithm. And that's it. That was the very last problem from 4.2, which is why I said 4.2 is fine to say is completed and homework is due. So again, there are times when we want to condense our logarithms. Generally speaking, we like condensing logarithms when we're solving equations involving logarithms. There are times when we like expanded logarithms. Generally speaking, we like to expand the logarithms when we're graphing or doing calculus. And I'm not going to say every time we're doing calculus that we need them expanded, but it's quite often that we do. And I can't really explain why that is in here. No, we don't have to worry about the order. This is just the most common order because I put the number, then the x, then the y. If you put the 3 in between the square root of x and the y squared, it's not wrong. It just looks awkward. It looks weird. It's kind of like having x3 instead of 3x. Okay, next section, which is the change of base, 4.3. 4.3. 4.3 change of base. How about when the problem is given? Your question of how about when the problem is given, I don't know that that helps me answer anything. That seems very vague. If you want to rephrase that, please do. But again, just because this 3 term was the second thing, it doesn't matter if we pull the 3 in the front because this makes it just look better. So it's the same thing as having the natural log of the square root of x times 3 times y squared. Like I said, this just looks awkward. We really like this 3 over here. About the order when the problem is given. No, all you have to worry about with the problem is that the positive logs or natural logs go in a top, the negative ones go in a bottom. These things can be shuffled around in any order you like. You don't have to worry about that. Okay, now I got it. So change of base, this is just a single formula. Actually, no, we're still in 4.3. What am I talking about? 4.3 was this all along. This is 4.3 continued. This is what happens when you're looking at a cell phone. You miss the word continued. Okay. Change of base. I mentioned something in passing previously, and I got to pull up my calculator. Let me pause the share. Da, da, da. Resume. Cool. All right, so we mentioned with our calculators, there are only 2, at least with most calculators, most normal scientific and graphing calculators, there's only 2 logs that they can evaluate. A log with a base of 10, so if I do log of 10, that should be 1, and it is. And a log with a base of e, the natural log. So that base is an e, so if I did the natural log of e, this answer should also be 1. Or if I did the natural log of e squared, this would be 2. So the bases match, so the whole thing's the exponent. And it's 2. What if I wanted to calculate, get a value? What if I want to have some type of grip on a number? So, oh, okay, the answer is the natural log of 7. Okay, what does that mean? What is the natural log of 7? Well, the natural log of 7 is 1.94, pretty close to 2. But if I had a log base 13 of 7, I can't put that in a calculator in that format to actually get the numerical approximation, because if we're talking about word problems, applications, we need a sense of the size of the number, then we do want to see a decimal rounded to the tenths or hundreds or thousands, whatever we want. It's nice for the algebra to have the exact answer of log base 13 of 7, but it doesn't give us a sense of the size of the value. So if we're supposed to be finding, well, how many items should this company to produce? How many items should this company produce to maximize its profit? And the answer is the log base 13 of 7. Your boss is going to go, you're fired. I want to know, an actual number. I don't know what a log is. Where did this come from? You're my math guy. Tell me something I can understand. So how do we punch something like that in the calculator? With this formula, the change of base formula. So the change of base formula, the last thing of 4.3. It says that the log with a base of b, and then there's some inside, some m. The m represents anything. You can make a ratio of 2 logarithms with a new base of your choosing. So let's go with a. So a is our new base, and we get to choose that. And then the insides of these 2 logarithms, for the top, it's the original inside. For the bottom, it's the original base. So again, you choose the value of a. If you want to do an a of 13, go for it. If you want to do an a of 17, go for it. If you want to do an a of 2,000,000.3, go for it. Me personally, I would say e and 10 are generally best choices. Why? Because calculators can handle those bases. So there are literally, whenever someone asks you to do a change of base, there are literally infinitely many answers. Because you might choose a base of 3, I might choose a base of 10, Bob might choose a base of 99, Jane might choose a base of 101, and they can all be correct. But in terms of actually doing numerical calculations to get the decimals so your boss doesn't fire you for being a math nerd or something like that, you're going to need the E or the 10. So when I do an example, I'm going to give you several versions of answers and tell you which ones I would prefer. So example 4, last set of examples for this section. Do a change of base. Now, if you are going to be doing the homework in 4.3, which again, I heavily suggest, pay attention because my math lab might say what base they want you to make it in. So please just pay attention. And it's another case of I've got too many programs from too many classes from teaching this in WebAssign and Connect, and some of them have requirements, some of them don't. It's a lot to keep track of, so read the instructions. For A, we're going to have the log base 7 of 10. So boss man says, all right, what's the value that maximizes our profit? And you say, it's log base 7 of 10, sir. And he goes, nonsense, I don't know what that means. I want a number. Is it 7? Is it 30? Is it 1,000,000? Is it 2? So you go, okay, well, let me get a calculator. And you can't put this in a calculator because you got a TI-83 in front of you. So you go, oh, right, Mr. Beckner said do a change of base. I can pick the base. Maybe I want a base of 2. Is that going to be helpful? Spoiler alerts, no, but it will still give us an answer. So I'm going to pick a new base of 2. So me picking a base of 2 automatically gives us this. We're going from a single logarithm to a ratio of logarithms. Now, this is not the quotient rule. The quotient rule took a log of a quotient. This is a quotient of logs. Those are opposite things. Now, when you want to say opposites, they're different things. Saying opposites is kind of a weak word there. Now, in these two logarithms, the top one gets the original inside, so this is a 10. The bottom one gets the original base. So this is a 7. And I am not going to verify this, this rule. It would probably take us 30 or 40 minutes to do the proof. And again, we don't have that time. So take it at face value. So this right here is an answer. This is perfectly fine because all I said was do a change of base. I didn't say what base to choose. If you make these 2's 3's, that's an answer. As long as they're both 3's, they have to match. You can make them 17s, you can make them 41s, you can make them pi's as long as they're a positive number. But this one kind of sucks because, again, the whole idea behind this is generally to have something you can put in a calculator, and I can't do a log base 2. So while analytically correct, it's not helpful for computation. So let's now show the answers that are better for computation, once with an E and once with a 10. Let's do the 10 first. So this would be log base 10 over log base 10. Now, since I'm making the new base as 10s, I don't write them. These are assumed to be 10s. And then the inside of the top one is the original inside, which is 10. The inside of the bottom is the original base, which is 7. Now, I'm not going to box this answer up because if you type this in a program or gave this to me on a test, it's wrong. This one is simplifiable because this top right here, log of 10, is one of those 4 properties from the beginning of 4.2. If the base, which is a 10, matches the inside, the whole thing is 1. So that's actually kind of convenient analytically because we now only have a single logarithm and it has a base that we can put in a calculator. So this, in my opinion, is a better answer than the last one because I can type this in a calculator. So we can now figure out what log base 7 of 10 is. It should be 1 divided by the log of 7, log base 10 of 7. And we get 1.18. Now, maybe you don't believe that these two things are equivalent. Let's do log of 10 divided by log of 7. Make sure you're closing your parentheses correctly. We get the same thing. Now, maybe you're going, okay, well, that doesn't prove anything because we never got to see what the log base 7 of 10 is. Well, maybe you'll believe me if I at least do the natural log versions and get the same decimal answer here. So the third or answer, and again, there's a million, a billion, a trillion different answers here. I'm only showing 3 because the first one, just make those 2's any matching number that's positive and you're good. So now let's do this with the base of e, but I'm not going to write log with a little base of e. I write ln's. So this is a log base e and a log base e, where the top is still the original inside, the bottom is still the original base. None of these bases match the insides, so that's the answer. So a third version, and this one is calculatable. So let's go natural log of 10, close it, divided by natural log of 7, close it. And you still get that 1.18 number. So I hope the fact that these last 2 things match gives you a little bit more faith that this formula is true. Now, if you can find a calculator out there that can do a log with any base, you could then verify it, but trust me, it's true. So analytically, the middle one's the best answer because we were able to simplify one of those 2 logarithms. But in terms of computation, the whole reason for a change of base, these 2 are both perfectly fine. You just can't leave, and this is where people will make mistakes, you can't leave the log of 10 there. You have to simplify it. Those are the most common mistakes with chapter 4 is people will apply one formula and then forget to simplify things that can be simplified. Let's try another one of these. 1 isn't enough, just like a Dorito. And we're going to go log base 3 of e. So I'll do one of them real quickly that has just a nonsense base. And this is where I ask a student, what's your favorite positive number? And I'm going to be the student and I'm going to say 42. So I'm choosing my new base as 42. Again, this would be whatever number a student picked in class, because you can make it any number. And then the top is the original inside, so that's an e. The bottom is the original base, so that's a 3. And there's our answer. But that's not helpful computationally. This is uglier, and you can't put it in a calculator, a standard calculator. So let's get the 2 better versions, one with a base of 10. So it'd be log base 10 of e over log base 10 of 3. These bases do not match, so nothing simplifies. That's as far as you can take it analytically. Or if you did a natural log, so a base of e, the top inside is the e, the bottom inside is the 3. If you circle this, that's incorrect because the natural log of e is 1. The bases match, so the whole thing is 1. That's 1 divided by the natural log of 3. So let's see our calculator to make sure that these work. We can't show the first one or the original problem. All I can do is log of e, close it, divided by the log of 3, close it. And we get 0.91. Let's see if the other thing gets us the same answer. 1 divided by natural log of 3. Same answer. So that's good. It's a good sign that it isn't just nonsense. That will finish up 4.3. So again, I'm only holding you responsible for the homework up to 4.2, but you will see 1 or 2 questions in the review that deal with 4.3, which means you will see 1 or 2 questions on the final that deal with 4.3. So again, I'm not holding you responsible for the homework, but I am holding you responsible for the material of this. I will even admit, I want to make an admission that I don't know this is true now. I don't think I put a change of base on the final. I'm pretty sure I didn't. I'm pretty sure I only did it up to the content that we had finished last class again for that 1 week learning period. Now we can get to a new section. 4.4, exponential and logarithmic equations. Why do we generally learn how to manipulate something? Generally to solve an equation involving it or graph it. Okay. So let's start out with the exponentials first, because we're used to exponentials, I feel like, a little more than logarithms. if you can make the bases match for an exponential equation, do so. If the bases match, the exponents must match. So we just set the exponents equal to each other. This is arguably the simplest case. Arguably because it might be a challenge making the bases match, and you can't always, and in fact, most of the time you can't. But if you can, this is the best approach. Example 1. Solve. For A, we're going to have 2 to the 4x minus 1 equal to 32. Okay, so this is an exponential equation. It's exponential because you see a base and an exponent. So if you can make the bases match, do so. So the left side's base is a 2. There's no way you can break that down anymore. The right side is 32. What I'm saying is maybe we can write 32 as 2 to some power. Well, if you go through multiples of 2, 2, 4, 8, 16, 32. That's the fifth one. So this becomes 2 to the 4x minus 1 is equal to 2 to the fifth. We have been able to make the bases match. Now, if the bases match, this is a 2, this is a 2, everything else has to match. So the 4x minus 1 has to be the same thing as 5. So what we're able to do is just set the exponents equal to each other. If the bases match, the exponents must also match. So we get 4x minus 1 equals 5, a whole new equation. A much simpler looking equation, which is nice. This is linear. It doesn't have to be linear. It can be quadratic. It can be any type of equation in theory, but I won't give you anything that crazy. I mean, it's not even on final, but we still need to see this stuff because you will see this in later maths. So you add 1 to both sides, you'll get 4x equals 6. If you divide both sides by 4, you'll get x equals 6/4, which is x equals 3/2. And that's our answer. B, 25 to the 3x equals 125 to the x plus 4. Okay, so this is exponential, and you already have 2 exponential pieces. Sometimes it's just 1, sometimes it's 2. It could be more than that as well. So let's see if we can make the bases match. Well, there's no way to write 125 as 25 to a power. Spoiler alerts. So it's not as simple as the last one. We need to break down both of these numbers. 25 is 5 squared, and 125 is 5 cubed. So the 25 is what I wrote in red, the 125 is what I wrote in red. But these still have exponents of 3x. Now, because this is going to have multiple exponents, we need to wrap that in a parentheses like so, and we need to write the correct number, which was 3x, not 2x. I was looking at the 2. Same thing on the right side, like so. Now, when you have a base raised to an exponent raised to another exponent, as a reminder, you multiply the exponents together. So for the left side, you'll get 5 to the 6x, because 2 times 3 is 6. And on the right side, you'll get 5 to the 3x plus 12. You got to distribute that 3. This 3 goes to the x, and it goes to the 4. Now the bases match, so what we can do is make a whole new equation, just using the exponents. If the bases match, the exponents must match. So that 6x has to be equal to 3x plus 12. Subtract 3x on both sides, and you'll get 3x is equal to 12. Divide both sides by 3, and you'll get x is equal to 4. And that's our answer. And you can feel free to check these. And the last one, 3/2 times 4, well, the 4 and the 2 will reduce to a 2. 2 times 3 is 6. 6 minus 1 is 5. And 2 to the 5th is definitely 32. The answers will be a little bigger here. And I don't know them off the top of my head. 25 to the 12th power, some ungodly large number. But it will be the same thing as 125 to the 8th power. You can trust me there. C. Oops. Color. 3 to the x is equal to 7 to the 4x minus 3. All right, so we got two different bases, two different exponents, so maybe we can make the bases match. Well, man, I'm having a hard time right here. 3 is prime, so I can't really change its base. 7 is also prime, so I can't really change its base. 21. So you're just trying to multiply these, but remember, we're trying to break these down to smaller things. So like the 25 we wrote as 5 squared. We need a smaller base with an exponent. There is no way to write 3 with an exponent besides 3 to the first. There is no way to write 7 as anything but 7 to the first. You can't match bases here. So for now, what do? We have no idea. Actually, we can't move on for now. I just wanted to do an example so that you could see the difference of when you can, like A and B, and when you can't. Does that mean it's not solvable? Absolutely not. It just means it's not under this, quote, easy case. So let's get into that case. What happens when the bases don't match? What can we instead do? When the bases can't be made to match, what you're going to do is follow the very first principle of algebra you ever taught with equations, which was whatever you do to one side, you raise his hands, ask the class, and they all say, do to the other. Whatever you do to one side, do to the other. You can do anything to an equation except divide it by 0, and maybe some other sketchy things that you don't know about yet, and some other sketchy things that I probably don't know about, because I don't know every single bit of math in the world. No one does. And if they tell you they do, they're lying. You can know a lot, but not everything. So we're going to do the same thing to both sides, and here's what we do. Take a log. Let me write that out. Take a log base B of both sides. So take a log with, in theory, any base. In theory, any base will solve the equation. In application, it generally works that any base. You can choose a base of 2. You can choose a base of 10. You can, I think I said juice. You can choose a base of E. You can choose a base of 17. You can choose a base of 1,000,000. And these are still going to create solvable equations. However, for us, in general, our approach in general is to take the natural log of both sides, unless there was a base of 10 originally. This is just the traditional technique, so that way you don't have 5 billion different answers possible. We just say, all right, if there isn't a base of 10, just take a natural log of both sides for consistency. But if you do see a base of 10, then take a log base 10, because that's going to help things simplify a little bit more. Is this the approach that I always use? Honestly, no. What I generally do is, like, let's say C was the example, and I'm not even going to complete C, but if C was the example, I would choose my base to either be 3 or 7, because that's one of the bases that we originally see. So for convenience in the real world, we usually choose one of the original bases, but in a pre-calc class for consistency, we just say take a natural log unless you see a base of 10. You can take a log base 10 of both sides. You can take a log base E of both sides. You can take a log base 3 or 7 of both sides and get different looking answers, but all the exact same, just like those change of bases have infinitely many answers. Solving these equations can have infinitely many analytic answers. So we just generally do natural logs or log base 10s. All right, example 2. Solve. Excuse me if you heard that. 5 equals e to the 3x. So the first thing when I look at this is I'd say, oh, can I make the bases match? And in about that quick, I'd say, no, I definitely can't make the bases match. There's no way to make e 5 to some power, and there's no way to make 5 e to some power using rational numbers. Notice I said using rational numbers. Math, you can manipulate things in unbelievable ways. Okay, so because this isn't under the easier set of examples, we're doing this new thing. Take a log of both sides. I don't see a base of 10 anywhere, so we're gonna say, let's take a natural log of both sides. So I'll, in red, show the step I'm taking. I am taking the natural log of the left side and the natural log of the right side. Whatever I do to one side, I do to the other. Did I break any rules? No. I certainly didn't divide by 0 here. So now we just solve. Well, how do we solve this? The reason we do this is because originally we had variables in our exponents. Now we're going to have a log of an exponential where the variable's in the top. Let's go back to the previous section, that power rule. Remember that the bases don't have to match. You can just bring the exponent out front. So if they don't match, you can apply the power rule. But if they do match, you can apply this top right property where the whole thing is just the exponent. So those are the most two common properties you'll use with these solving equations. You'll either have the bases match, so the whole thing is just the exponent, or if the bases don't match, you bring the exponent out front, which will get your variable out of a logarithm and out of the weird thing that we don't really have a great grasp of yet. So here, the right-hand side, RHS means right-hand side, RHS means right-hand side, the bases match. That's a natural log base e, this is an e. So that says that on the right-hand side, the whole thing is just equal to the exponent. You can bring it out front, but then you'll have a natural log of e next to it, which is 1, and you still just get the 3x. The left-hand side, the natural log of 5 is the natural log of 5. Got no idea what it is. It's just a number. If you want to know what it is, you can put it in your calculator and get a decimal approximation, but we're not going to do that. Now, we're supposed to solve for x. There's only an x on the right-hand side. I don't care what this natural log of 5 is. This is just a number. So this says 10 equals 3x, or 20 equals 3x, or 1,000,000 equals 3x. What do? You divide both sides by 3. So, because this says 3 times x, we divide both sides by 3. And that's going to give us, the 3's will cancel, and we get as an answer the natural log of 5 divided by 3 is equal to x. Now, if they ask for a decimal approximation, then you would do that too. I can't tell you when problems do and don't. It depends on which homework problem you're working on. But generally, we prefer the analytic answers. It may ask for the analytic answer, which is this, and the decimal approximation. So maybe you're curious exactly what approximately this number is. So you could type natural log of 5, close it, divided by 3, and that says that x is about a half. 0.54, depending on where you round. But again, I'm usually not interested in the decimal answer. I'm much more interested in the analytic answer. Okay. Something I need to point out before moving on. Let's say we had, I'm just going to put this up here. Let's say we had the natural log of 6 divided by 2. What some people will think is, oh, 2 goes into 6 3 times, and this is equal to the natural log of 3. I wrote 3 twice. And it's not. It is wrong, 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 wrong. You cannot reduce insides of logarithms with outside numbers in the same way that you can't reduce insides of square roots with outsides of square roots. because you have a function happening here that's not happening here. That's inside, that's outside. You can't reduce things like that. So please be aware. I see a lot of students want to try and simplify things that are not simplifiable. These answers can be really muddy looking. So this example was really nice because by taking the natural log of both sides, because there was a base of e originally, it simplified this really quickly. It made less arithmetic and algebra necessary. B, let's do 17 equals 10 to the 4x minus 5. Now, there's no way to make bases of 10 and 17 match. You can argue with me all you want. You can't do it using rational whole numbers. So we need to take some type of logarithm of both sides. Now we said, generally we take a natural log unless there's a base of 10 somewhere, which I see. So it would be better for us to take a log of both sides. So here's me taking a log of the left. Here's me taking a log of the right. And let's write all that stuff in there. Is it wrong to have taken a natural log of both sides again? No, but you won't see one detail of simplification that you will in this version. Let me just move this little parentheses a little bit. There we go. That looks better. So again, the reason we do this is so that we can bring variable exponents out of logarithms. So the left side's log of 17. The right side, the bases match. It's a 10 and a 10. So all of this stuff cancels except the exponent, which is 4x minus 5. We will see an example where those things don't cancel. All you can do is bring the exponent out. Don't you worry. Now again, this log of 17, this is just a number. This right here is 4 or 90 or 1,000,000 or 3.7, whatever it is. It doesn't technically matter. It's just a number. Focus your attention on the sides with the variable, side with the variable. And there could be variables on both sides. Maybe we'll see that. So our attention's focused on the 4x minus 5, which tells us we need to add 5 to both sides, and then we need to divide by 4. So we're going to add 5 to both sides. I'll show the work. Add 5, and I'm going to kind of squeeze this in there, so it's not directly under the log. So this is the log of 17 plus 5. Don't add them in the same reason you can't reduce these. This is an inside, this is an outside. Insides and outsides can't cross-communicate. So that gives us our 4x. Then because that says 4 times x, we know we need to divide both sides by 4. So divide both sides by 4. So we get the log of 17 plus 5 all over 4 equals x. And that's our answer. Nothing simplifies here. 5 and 4 do not reduce. The 17 cannot combine with the 5 because that's the inside of the log. What some people might want to do is actually put the 17 in parentheses for clarity. What some people like to do is make sure they write the whole number first. So 5, then plus log of 17 over 4. That would be an equivalent answer. And it makes you less likely to combine the 5 and 17, I think. At least it does with me. Now again, you might be curious as to what that is approximately. So you pull up your calculator. The homework might even ask for it. 5. Let's go parentheses. 5 plus log of 17. Close that parentheses. Close the second one. Divided by 4. So make sure the calculator gets the order of operations right. And it's about 1.5 roughly. 1.6, 1.56, depending on where you're told around to. All right, so maybe you think you can combine the 5 and the 17. So let's try the log of 22 divided by 4. If you can combine the 5 and 17, this should be 1.55. And it's not, so there's your proof. Same thing, here's that natural log of 6 divided by a 2. Here's the natural log of 3. If you thought you could reduce it, definitely a different answer. All right, C. Is this the same one we had earlier? No, it's close though. Close enough. We're just making a point with that question mark example. You can go back and solve it, but I'm not going to. 13 equals 7 to the 5x, because this problem is similar enough. Now this one does not have a base of e or 10, so the answer will admittedly be slightly uglier, but it's not a problem, it's just an uglier answer. So there's no way to write bases of 7 and 13 as the same base, so we take a log of both sides. No matter what type of logarithm, log base 3, log base 8, log base 2 million, log base e, log base 10, it all will get a correct answer. Since we don't see a base of 10 though, we choose to take a natural log of both sides, just for, again, consistency. So it'll be natural log of 13 on the left, natural log of 7 to the 5x on the right. Now, this base on the right is an e for the natural log, this base is a 7, those bases don't match, so this whole right side is not just 5x. We have to bring the exponent down since the bases don't match. Again, that was the power rule right here. If the bases don't match, you can still take the exponent and bring it out as a product, as a coefficient. So we're going to get the natural log of 13 is equal to 5x times the natural log of 7. Now, focus your attention just on the side with a variable if there's only one variable. So we're focusing here. That x is just multiplying by a number. It's multiplying by 5 and natural log of 7. So to get rid of those multiplications, what do? We divide. So what we do to solve this is one step. We divide both sides by 5 and the natural log of 7. That's just a number, 5 natural log of 7. We do that because the 5s will cancel on the variable side, the natural logs will cancel on the variable side, leaving us with our x by itself. So what we get is the natural log of 13 divided by 5 times the natural log of 7 equals x. And that is our answer. Again, one of the infinitely many possible answers, but the one that we say to do for consistency. So here's that quote complication I mentioned. When you don't have matching bases, you just bring the exponent down in front instead of having all those cancel. Excuse me. In the last two problems, because of the more cancellation happening, there was only a single log in the answers, whereas in this one there's two. Whoop-de-doo, right? Does that matter? No, just an uglier answer. If you want the decimal approximation, you can do that. Natural log of 13, close your parentheses, divided by. Open a parentheses, 5 times the natural log of 7. If you don't open that parentheses first, it's going to be wrong. And it's about 0.26. Maybe you don't trust me. No one trusts me. Natural log of 13 divided by, I'm kidding, some people trust me, 5 natural log of 7. Maybe you think that denominator doesn't need that extra parentheses. I'm going to tell you that answer is wrong. Just think about this. If this answer was correct, that number is pretty much 1. So if you put in a 1 here, that says that 7 to the 5th power is the same thing as 13. That sounds like a very obvious lie. But if your exponent's about a quarter, that makes this about 1.25 roughly, and 7 to the 1.25 power is probably close to 13, if not exactly 13. So think about the size of things when you can, if you have decimal approximations that you can relate to. But you're not going to be able to relate anything looking at the analytic answer. That's weird. Oh, there it is. Okay, there's my D. Let's go to the next page. Let's do another one. How are we on time? 2:30. 5 to the x minus 2 is equal to 4 to the 2x plus 3. Yeah. So this one's different than the previous 3. How is it different? The previous 3, one of the sides was just a number. There was only an exponential on one side. This has got exponentials on both sides. Again, first thing you want to typically try is making the bases match. You can't make a base of 5 match a base of 4. 4 you can write as 2 squared, 5 you can't do anything to. So we're stuck with this. Take some type of a logarithm of both sides. Technically speaking, the base won't matter. I would, in my opinion, my own work, I would do a base of 5 or 4, but just E is what we tell our pre-calc students to do. So I'm going to take a natural log of both sides to follow the rules that you are supposed to. Again, it's not a stern rule. You can take any logarithm of both sides. We're just doing this for consistency among students. Okay, so there's us taking a logarithm, specifically a natural log of both sides. Now we can bring the bases down, bring the exponents down. Taking the logarithm basically cancels the exponent of the exponential because we can bring it down as a coefficient. That's like that. It's like adding when you see a subtraction, or multiplying when you see a division. When you see an exponential, you logarithm. And then that tells you that if you saw a logarithm, you could exponentiate both sides, even though it's not what we usually do. Don't worry, we'll see what we usually do. So the x minus 2 is going to come out in front. Now notice that the x minus 2's got multiple terms, so I can't just do this. If I just write the x minus 2 in front of the natural log of 5, that only multiplies the minus 2. So you're going to need that in a parentheses. Same thing on the right side. You're going to need the 2x plus 3 in a parentheses, and then times the natural log of 4. Now we got variables on both sides. This is a much more complicated equation than the previous 3. Because we have variables on both sides, we need to ultimately get all the variables on one side and any term that doesn't have a variable on another side. This is the third different scenario in this course that we've come across this situation. And we first introduced it back in the formulas section, the literal equation section. And then we saw it pop up again later. Oh geez, I can't even remember when, but we saw it again later. So to do so, because there's an x inside of parentheses and an x inside of parentheses, we're going to have to distribute here. What are we distributing? The natural log of 5 and the natural log of 4 backwards to those parentheses. Distributions don't have to go forward, they can go backwards. So this will be x times the natural log of 5 minus 2 times the natural log of 5 equals 2x times the natural log of 4 plus 3 times the natural log of 4. Then we collect the x terms on one side, and then all others on the opposite side. Come on. Classic technique. It does not matter which way you move them. It does not matter which way you move them. I'm looking at this as a 2x and this is an x, so I'm going to choose to move them right. That's kind of an arbitrary choice. So I'm going to subtract the x natural log of 5. Again, this is just a number. This is like subtracting 4x or 8x or 7x or 5x. It just looks a little goofier. Now again, I'm going to put it here, even though, spoilers, I'm not going to be able to combine that. So all my variables are going to the right side. I've chosen that. You can move them left, which means you would be subtracting the 2x natural log of 4 instead. Now, because the variables go right, anything that's not a variable is going to have to go left. Now, I'll do that in a different color. So the 3 natural log of 4 needs to move. That's being added, so we subtract it. And again, I'm going to put it under something I really shouldn't. I'm not going to be able to combine the black and the blue. You'll end up bruised otherwise. Sorry, terrible joke. I just don't have the room to put it anywhere else. So what happens? These things cancel. These things cancel. On the left side, we have negative 2 natural log of 5 minus 3 natural log of 4. Make sure you don't think those are 21s and 31s. If you have to put a little dot next to them, you can, but I'm not gonna. Then equals, that's going to be 2x natural log of 4 minus x natural log of 5. Now we have all our variables on one side. This has got an x, this has got an x. All the other terms are on the other side. These don't have x's. This is when we factor out a GCF. That is the variable we're solving for. This term has an x, this term has an x, so let's factor it out. The left side doesn't change. Factor out your GCF, and then just all those numbers are left over. 2 natural log of 4 minus the natural log of 5. And no, the natural log of 4 minus the natural log of 5 is not the natural log of -1. You can't even do that because of the coefficients. You can't do that because the insides match. There's lots of reasons you can't combine that. Now the variable's still on the right side. Focus your attention on the right side. I don't even care about this side right now. This, as ugly as it looks, is just x times 5, or x times 7, or x times 10, or x times 1,000,000. This is x times some funky number that we don't know what it really is, but it's just x times a number. So how do we get rid of x times a number? That's right. We divide both sides by the number. So we're going to divide by that parentheses with the x. So we divide by the 2 natural log of 4 minus the natural log of 5. So that that whole entire thing cancels on the right side. And the left side is what it is. It's not pretty. There's literally nothing you can do to simplify this. It's -2 natural log of 5 minus 3 natural log of 4 over 2 natural log of 4 minus the natural log of 5. And that is our answer in all its glory. Please note, there are many acceptable answers for this. You can factor a negative out of the top and go negative parentheses and then 2 natural log of 5 plus 3 natural log of 4. You could have moved the x's left and the constants right, which means you would have ended up dividing by a negative, and the negative can now be in the bottom. You can swap the orders of terms as long as you take their signs in appropriate orders. So you can write the -3 natural log of 4, then the -2 natural log of 5. You can write the minus natural log of 5, then the +2 natural log of 4 in the bottom. There are lots and lots and lots of acceptable versions to this answer. The point is, we got an answer. Now, if you were asked for a decimal approximation of this one, you gotta be very careful typing that in. So that whole top, you're gonna need to put in a parentheses. So this is the parentheses for the top. -2 natural log of 5, close, minus 3 natural log of 4, close, close. So I had to close each logarithm and then close the parentheses for the top. Then divide it by, open another parentheses for the entire bottom, 2 natural log of 4, close it, minus the natural log of 5. Close it, close it. And there's our answer. Again, as a decimal approximation, I'm much more interested in the analytic answer, the thing with the logs and the 5s. I honestly don't care about the decimal approximations unless it is an application. But I'm not saying that you won't see that in the homework. I'm just saying what I personally prefer. My math lab, be darned. So let's see another type of exponential equation. And I'm only going to do one of these in the interest of time. If you have a 3-term exponential equation, try to factor it like a quadratic. And then use a substitution to make that happen. All right, example 3, and it's supposed to be A, but we'll just do the first one. E to the 2x minus 5e to the x plus 4 equals 0. And per usual, everything doesn't already have to be on one side. You may have to set that up. Now I said, if you have a 3-term exponential equation, 1, 2, 3 terms, try to factor it like a quadratic. Notice I said try, I'm not guaranteeing it. Specifically, remember, for something to be quadratic, the first term, the exponent has to be twice the exponent of the middle one. That's a 2x, that's an x, 2x is twice this one. So this is quadratic in form. So we'd say let u, or whatever letter you like besides x, equal, and e wouldn't be a good one either, e to the x, which makes u squared equal to, and I'll show the work for this in case you get confused as to where it comes from. That's e to the x squared, which you just multiply the x and the 2, so that's e to the 2x, which is the same thing as the first term. So when we do this substitution, the first term becomes u squared minus 5, the second term becomes a 5u, and then a plus 4, and then there equals 0. And then from here, we just solve it by factoring quadratic formula, whatever you have to do. This is factorable. Factor pairs of 4 that add to 5 are 1 and 4. To make sure they add to a negative, they both need to be negative. So we go u minus 1 times u minus 4 equals 0. U minus 1 and u minus 4, I know my u's can look like 4's. Set each of these equal to 0. You get u minus 1 equals 0, and u minus 4 equals 0. Add 1, add 4, you get u equals 1, and u equals 4. Don't box these up, don't ship these out. These are not the answers. Remember, a substitution is us going from the dollar to yen. I want my answer in dollars, not yen. And we saw back in chapter 2 or chapter 1 that just because you have 2 answers in one format doesn't mean it's 2 answers in the other format. It might be 4 answers. It might only be 1 answer. If you have something that you need to check, you got to make sure you're checking. So now we go back to x by plugging into the let statement. We use this. We're going to plug the u into that. So we'll plug 1 and 4 in separately, not into the x, into the u's. So we go 1 equals e to the x, or 4 equals e to the x. Very Pink Floyd looking x on the left side. Well, that gives us an equation to solve on both of those, and we're going to solve them very similarly. You're going to take, we just worked on this, the natural log of both sides. So we go, the ln of 1 equals the ln of e to the x, or the ln of 4 equals the ln of e to the x. Well, the natural log of 1 is 0. So for that first equation, the left side 0. The right side, the natural log of e to the x is x. The bases match, so everything cancels. X equals 0 is a solution. Crazy, kind of. All this ugly, might think complicated work, and then 0 is an answer. Just seems too simple, but it is. The natural log of 4, we can't really do anything except write it as the natural log of 2 squared, which we do prefer now. The natural log of e to the x is once again just an x. Now we can bring the 2 as an exponent out front to get 2 natural log of 2 equals x. So those are our 2 answers. Now, before we move on, I want to point out an important memo. Make sure I got space. So, important memo. We can't take a log base b of a negative or 0. Or you can also just say a non-positive number. In other words, for every log of a log base b of some, let's say a must be bigger than or equal to 0. or else it's undefined. Why is that? Go back to the graph of a logarithm. We had that point 1, 0. And I'm only doing this for a base bigger than 1, but the graph had the same thing going on. There was an asymptote at x equals 0, so you can't use 0. This graph is nowhere on the negatives. So that's why. The domain of a logarithm is only the positive numbers. So you can't take a log of a non-positive. You can't take a log of 0. You can't take a log of a negative. You can only take logs of positive numbers. And that's true no matter whether the base is between 0 and 1 or bigger than 1. I'll show the other one for fun. We still had the 0, 1, but it came from above and it had slow negative growth. So that was when the base was between 0, and 1. So that's an important memo, because every now and then, maybe we were trying to solve this last equation. Maybe we ended up getting x equals the natural log of -7. You'd have to know to throw it out because it doesn't work. It doesn't make sense. -7 is not in the domain of a logarithm. And that can happen. And if you go and do the homework for 4.4, it will happen. If I was testing on this, I would give you one of those, but I already said I won't, given the circumstance, the situation. I just combined two words. So that's a very important memo that you should remember that will be an issue in calculus. All right, about 20 minutes. Logarithmic equations. So just like the exponentials, we kind of have an easy case and a hard case. Same with the logarithms. If you can simplify to just some log base b of m equals c. In other words, if you can simplify one side to be a logarithm and the other side to be a number, so you can't have two logs, or if you do have two logs to begin with, you need to condense them. It's a very common technique. But if you can make this just a single logarithm equal to a number, then you can easily convert to exponential form, which would be, for this one, b to the c equals m. I need to scroll down. That's nothing new. We did a ton of those in the first section. Remember that the part that's alone in one version can't be alone in the other, and the bases are always the bases. I just spilled a little water. Luckily not on my computer. And only a small drip. But it is where my mouse goes, so I need to clean that. Give me about 20 seconds. All right, so let's try these out. Example 4. Solve. A. Log base 3 of x minus 4 equals 2. Yes. Okay, so starting out easy, of course. I know that's a relative term, but easier than the rest. So if you can have this just be a single logarithm equal to a number, and it doesn't matter if the log's on the left side or the right side, it's just a log on one side and a number on the other side, convert it to exponential form. Now you can say to exponentiate both sides, so make these the exponents and then you get to choose a base. Personally, I'd choose a base of 3 to make things simple. But it's just not a technique that people really use, even though it does work most of the time. It's not something we do, generally speaking. We just go ahead and convert the form if we can get this nice special case. So when we convert this form, we're going to go to 3, that's our base, so this will be the new base, so they'll have its exponent of something, equals, now remember the part that was alone can't be alone again. The 2 is alone here, which means it cannot go here, It has to be the exponent, meaning the x minus 4 is the other side. This is so much better. We went from having a variable inside of a logarithm, which we barely even have a context with, but now we have an exponential equation where the x is just over here, and all you gotta do is add 4 to both sides and you're done. Well, first of all, the 3 squared is 9. You should probably do that first, but you could cram it all in one step if you wanted. Add 4 to both sides. I'll show that in black. Not that I really should at this point in pre-calculus, but you get that 13 is equal to x. Now, when you're solving logarithmic equations, we just said that you can't take a log of a non-positive. So you are arguably supposed to check every single logarithmic equation. You are arguably supposed to check every logarithmic equation. So you put 13 in, 13 minus 4 is 9, but you're not always going to be able to say definitively that the left side matches the right side. So what I mean by check is, make sure that you don't end up with a logarithm of a negative. Well, again, 13 minus 4 is 9, that's positive, so this is okay. Let's pretend for a second the answer was negative 13. Negative 13 minus 4 is negative 17, and that is us putting a negative in a logarithm, which is not fine. That solution would not be valid. So again, you really should check, and by check I mean make sure you're not taking a log of a negative every logarithmic equation. All right, B. We got 7 times the natural log of 3x is equal to 35. So as long as we can get it in a form, a log equal to a number, we can use this process. Some people will say, oh, this is in that form, so I go e to the 35 equals 3x or something like that. But this 7 right here complicates things. Not saying it breaks things, it complicates it. We cannot switch forms yet. We need to get rid of the 7. Well, we want this to be by itself. This is the thing we want to be by itself, so we need to get rid of the 7. It's multiplying, so we divide it. So let's divide both sides by 7. So that the 7's cancel. They're not inside and outside of a log, so we can cancel. It gives us the natural log of 3x is equal to, and 35 divided by 7 is 5. Now we can switch to an exponential form. The base is assumed to be an e, so this base is an e. And we have our equals. There should be an exponent on the e. The 5 was by itself before, so it can't be by itself again. It is the exponent, making the 3x the thing that's by itself. The base is never by itself. E to the 5th, well, 3 squared we said was 9, but e to the 5th is just e to the 5th. It's a decimal otherwise, so leave that alone. You might say, oh, well, what do we do? Well, that says 3 times x equals a number. We don't even care what number this is. We just know since it says 3x, we're going to divide by 3. So divide both sides by 3, so they cancel, giving us on the right side just our x, and on the left side, e to the 5th divided by 3 is e to the 5th divided by 3. Sure, you can get a decimal approximation to it. I generally don't want it, though. Honestly, to do my last example, I probably need about 15 minutes of discussion just to set it up, or 10 minutes of discussion. Yeah, we're not going to have time to do that because the last example is significantly more challenging than these last two. So I'm actually going to call it there. Man.
All right, everyone. So once again, you have your dates, you have your expectations. Per usual, email me with any questions, please. And again, I hope you have a good rest of your semester. I hope you all have good luck with your exams and enjoy your break between, and maybe we'll see you in the spring. Take care, everybody.